So the sum, so the way we look at these, this is called sigma notation, this big Greek letter here, in case you don't know, is sigma. It represents, did you get it?
I thought I was hallucinating.
That's the Greek letter sigma. It's used in math quite frequently to represent the sum of something. Okay, so if we look at the notation here, this is, whenever you're looking at a summation here, this bottom number, n equals 1, is always going to represent the starting value of n. Okay, that can also be you could think of it as your starting term. Okay, and then that value at the top where k is your maximum value or your ending term. And what it means is you're taking a value of n equals 1 and you're plugging it into whatever the function is here. Okay, and then you're going to plug in 2, and then you're going to plug in 3, all the way until you reach k. Okay, and it'll make more sense when we actually do some with values.
Wait, so n is expression for what?
It's like your function, f of x. So expression for the general term is what it says there. Okay, so you could do, if you had something like the sum as n equals 1 all the way up to k of my a sub n could be 2x plus 1, right? So if I plug in 1, I get 2 times 1 plus 1, which is 3. Plus, if I plug in 2, I get 2 times 2 is 4 plus 1, which is 5. Plus, all the way up until I plug in k. Okay? And if you added up all of those terms together, that would be the summation of 2x plus 1 from n equals 1 to k. Okay? In the bottom there, it's just kind of indicating what I just explained. All right? So k can actually have an ending term. It can have a value that ends. So, for example, if I did the sum of n squared plus 1, n starting at 2 and ending at 5, I'm going to plug in 2 for n, plus I'm going to plug in 3 for n, plus I'm going to plug in 4 for n, plus all the way until I get to that last value. Okay? So what does that give me? 5 plus 10 plus 17 plus 26 and whatever that is. Okay? 58. Thank you. Okay? Does that make sense? Are there any questions? All right, let's try more. Or a few more. Write each expression in expanded form and then find the sum. So the expanded form is what we did when we plugged in each of the values and just wrote it out the long way. Okay, so in this case, that's going to be, oh, this is similar to the one we just made up. 1 squared minus 3 plus 2 squared minus 3 plus 3 squared minus 3 plus 4 squared minus 3. Okay, so we could figure these out, right? 1 squared minus 3 is negative 2 plus 4 minus 3 plus 9 minus 3 plus 16 minus 3. And if we add those all up, we get 18. Yeah. Mm-hmm. If we do the first few terms, we're going to have 5 times negative 2/7 to the 1 minus 1 plus 5 times negative 2/7 to the 2 minus 1 plus 5 times negative 2/7 to the 3 minus 1. We get the idea? Mm-hmm. Plus dot, dot, dot. Okay? So if I simplify that, anything to the 0 is 1, so I get 5. Minus 10 over 7. Plus 20 over 49. Minus, oh, we didn't do another one. Yeah.
Why are we finding the sum of this?
That's the point of sigma notation, is finding the sum of a sequence or a series.
But like, are we going to use that for anything else?
Ultimately, in calculus, what you're doing, like these are all leading to limits, which we started to do before. And when you use the summation of a bunch of values, you're finding a limit, basically. And then in calculus, it gets into deriving and integrating, finding the area under a curve, maximizing values. I could go on and on, but yeah, it gets used ultimately. So in this case, it's alternating, right? What is our common, so we know that this is going on and on to something, right? So if I want to find the sum, and I know that this is a geometric series because we're constantly multiplying by something, negative 2/7, right, to get to the next value. So I can say that my common ratio is negative 2/7, and I can say that my infinite, how do I get a darker green? Is that one? Yeah. Okay. Infinite geometric series has an equation for the sum, right? We learned that the other day. It was A1 over 1 minus R. This helps us because we know what A1 is now, right? And we know what our common ratio is now. So I can actually just plug into there to figure out what the sum of all of these values will be, even though it's infinite and we don't want to sit there doing it forever. Okay, so 5 is my first term, negative 2/7 is my ratio, and so I get 35 over 9. Okay? Express the series 15 plus da, 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 all the way up to 143 using sigma notation. So we have all of these values, 15, 24, 35, 48, all the way up to 143. I need to figure out some sort of equation that I could plug in a value in order to get these numbers, right? So, for example, what's going on each time? Do we see any sort of pattern?
I see a pattern, but I don't know how to explain it.
Okay, oh, you don't know how to explain it.
Well, yeah, you add 2 to the odd. You start at 9 and then add 2 each time. You add 2 to 9 and then you add to the previous term.
You start at 9, you add 2 to 9.
Yeah, because like 15 to 24 is 9, 24 to 35 is 11,
Oh,
35 to 48 is 13.
okay.
It'll be 15.
I gotcha. So something's going on there and it's increasing each time.
Yeah.
Okay. So, what if, oops. What if you had something like, they're almost perfect squares. I should have picked an easier one to start with. This is like if you did 4 squared plus 4 squared minus 1.
Oh yeah, perfect square is -1.
Right? This one could be 5 squared minus 1. This one could be 6 squared minus 1.
So the final one is, it's going to be Kate.
Wait, so you would just figure this out by sort of
N
like
equals
guessing
1.
and checking?
You what?
N equals 4 and then the top value is 12.
Okay, so this is 12 squared minus 1. Good. What did you ask?
Like, so you sort of find this out by guessing and checking?
Kind of. So Dimitri was on the right track. Like, you definitely want to look for patterning.
Okay.
So the easiest to start with are common sums and common ratios. Are you able to add something consistently each time? Are you able to multiply by something consistently each time? That's where you always want to start because it's the easiest. If you can't get to something from there, know that they're giving you some sort of pattern here, so you have to figure out what it is. In this case, if I had to write it in a general term, how can I write this?
In sigma notation.
Sure.
The sigma sign, then above it's going to be 12.
Okay.
Top is going to be 12, on the bottom it's going to be N equals 4.
Or- And what's the function?
N squared minus 1.
Right, so we're going to do the sigma notation of n squared minus 1, and you can see with each of these, this is my n value, right? So I'm going to say from n equals 4 to n equals, or to 12. Perfect. Okay. And that is the hardest part of everything.
So did you like know instantly that it was this? Or did you just...
No. No, you have to kind of play around with it.
Yeah.
You know, there's certain things that show up a lot. There's a lot of times there's stuff that's squared or cubic. There's a lot of times things will alternate. If you want a value to alternate, you can always multiply by -1 to the n. Okay, because if you plug in 0, you get 1. If you plug in 1, you get -1. If you plug in 2, you get 1. If you plug in 3, you get -1. So if these values were alternating and it was 15 minus 24 plus 35 minus 48, right?
Yeah.
Then you'd be able to say the sigma of -1 to the n times n squared minus 1. N equals 4 to 12.
Okay.
Okay?
I can take that later.
If you want me to. A factorial is something like this. It's not 4! It means 4 times 3 times 2 times 1. Okay? So that's called 4 factorial. N factorial, you start with n, then the next one's n minus 1, and the one after that is n minus 2, and it goes all the way until 1. And by definition, 0 factorial is 1. So we have 0 factorial, which is 1, 1 factorial is 1, 2 factorial. Good. 3 factorial. Good. 4 factorial. Yeah. So if we were looking at a value of numbers, we could say 2, 6, 24. I could keep going, 120, 720. This is 5 factorial. This is 6 factorial. So if you see some sort of pattern like this, it's hard to see how they compare, but that's, that's also a possibility that you have a factorial. Okay? So the reason why I'm saying that is because if you look at these values, 2, 6, 24, 120, 720, if you look at the next example, that's exactly what my denominator is here, right? So already I know that I'm going to have some sort of factorial value there. What else is going on? It's alternating, right? This is plus, this is minus, this is plus, this is minus. Okay, so already if I go to write sigma notation, I know that I'm going to have to do some sort of alternating something. So it's going to be either -1 to the n or -1 to the n plus 1. Sometimes we have to add to 1. I need to figure out the pattern in the numerator here. How can I get to that? What's going on with the numerator?
It's multiplying by 3 and then 4, and then 5, and then 6. So it's like 2 times 3 is 6, 6 times 4 is 24, 24 times 5 is 120, and 20 times 6 is 720.
Okay. So you're multiplying your numerator to your denominator to get the next numerator.
What?
I think you're talking about the denominator.
Yeah, you were talking about the denominator?
Yeah.
I'm talking about the numerator.
Oh, I'm sorry. I wasn't realizing. Sorry, I just said.
Okay, so that works, but what's the numerator now?
You just add 2.
Yeah, so in sigma notation, if you're adding 2 each time, it's better to think of it by multiplying each time. Okay, so how can I represent that?
Multiplying by
The number,
Before.
we'll call it n, by 2, right? So I could say 2n. And then that denominator, we know is a factorial value, right? If we go back a page, what we want to do then is take that into consideration. So that's going to be an n plus 1 factorial. So in other words, if I plug in n equals 1, if I plug that into my sigma right now, am I getting 2 over 2? Well, I have -1 to the 1, which is -1. So already I'm off because I need it to be positive. So I can change my a sub n of my f of x, my sigma notation, right? If I add 1 here in the exponent and I plug in 1, then it's going to be positive, right? And 2 times 1 over 1 plus 1 factorial gives me 2 over 2. So we're good. Let's just check on the next one to make sure. So if I plug in 2, I have -1 to the 2 plus 1, 2 times 2 over 2 plus 1 factorial. So this gives me -1 times 4 is -4 over 2 plus 1 3 factorial, which is 6. So -4, 6. So we're good, right? And if that was true when n equals 1, and this one is true when n is equal to 2, then this is going to be true when n is equal to 3, 4, and 5, right? So my last value above the sigma is going to have to be 5.